Problem Introduction. Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem 35, Search Insert Position. This is a medium-level problem, often popping up in coding interviews, so mastering it is a definite advantage. The problem statement asks us to find the index where a given target number should be inserted into a sorted array, maintaining the sorted order. If the target already exists, we return its index. If not, we return the index where it should be inserted. Sounds straightforward, right? Let's dive into the specifics. We're given a sorted array of integers, nums, and a target integer. We need to return a single integer representing the insertion index. Think about it. We're essentially searching for the target, and if it's not there, we're finding its correct position within the sorted sequence. The constraints? Well, the array length can range from 1 to 10,000, and the integers themselves are within a reasonable range. Let's get started with some examples to solidify our understanding. Understanding with examples. Let's walk through a few examples to make this crystal clear. Imagine our sorted array, nums, is 1, 3, 5, 6. If our target is 5, the function should return 2, because 5 is already present at index 2. Simple enough. Now, let's say the target is 2. 2 isn't in the array, but if we were to insert it while maintaining the sorted order, it would go right before the 3, at index 1, so the function should return 1. One more example. Let's consider the target to be 7. 7 is larger than all elements in nums, therefore it should be inserted at the end, resulting in index 4. Understanding these examples is key to designing our efficient solution. We'll see how both a brute force and an optimal approach handle these scenarios, but for now, let's move on to exploring a less efficient but illustrative method. Brute force approach. A simple, albeit inefficient, way to solve this is using a brute force approach. We can iterate through the array, element by element, comparing each element with the target. If we find the target, we return its index. If we reach the end without finding the target, we need to determine where it should go. We can check if the target is smaller than the current element, indicating that its insertion point is before the current element. This approach has a time complexity of O of n, meaning the time it takes increases linearly with the size of the input array. This isn't ideal, especially for large input sizes. It's straightforward, but not optimized. We can do much better using a more efficient algorithm, so let's explore the optimal solution next. Optimal solution. The optimal approach uses binary search. Since our input array is sorted, binary search is perfect. It allows us to significantly reduce the search space at each step. We start by examining the middle element. If the target is equal to the middle element, we found it. We return the middle index. If the target is smaller, we focus our search on the left half of the array. Otherwise, we search the right half. We repeat this process until we either find the target or narrow down the search space to a single element. If we don't find the target, the index of the element where the target should be inserted is simply the index of the last element we examined. This dramatically improves our efficiency. Let's see how this works in practice with our examples. Code implementation. Let's see the code in Python. We'll implement the binary search approach. First, we define our function that takes the sorted array, nums, and the target as input. We set up our left and right pointers to mark the beginning and end of our search space. Next, we enter a while loop that continues until the left pointer crosses the right pointer. Inside the loop, we calculate the middle index. If the target equals nums at position middle, we found it. We return the middle index. Otherwise, if the target is less than nums at position middle, we move our left pointer to the middle plus 1. If the target is greater, we move our right pointer to the middle minus 1. Finally, if the loop completes without finding the target, the left pointer indicates the correct insertion position, and we return that. This concise implementation showcases the elegance and efficiency of binary search. Time and space complexity. The beauty of binary search shines through its time and space complexity. The time complexity is O of log n, a significant improvement over the linear O of n of the brute force method. This means the time taken increases logarithmically with the size of the input, much faster for larger arrays. The space complexity is O of 1, constant space, because we're only using a few variables to track our pointers and index. No additional data structures are needed. This makes it incredibly memory efficient. We've successfully reduced our complexity, making our algorithms suitable for handling larger datasets efficiently. Engagement break. So, there you have it, a clear understanding of how to effectively solve the search insert position problem. Before we wrap things up, don't forget to smash that like button if you found this tutorial helpful. And if you want to see more LeetCode problem solutions and algorithm tutorials, hit that subscribe button and ring the notification bell so you don't miss out on future uploads. Also, leave a comment below. Let me know which LeetCode problem you'd like me to tackle next. Your suggestions fuel this channel's content. Conclusion. To summarize, we've covered the search insert position LeetCode problem, exploring a brute force approach, and then diving deep into an optimal solution using binary search. Remember the key takeaways. Binary search excels when dealing with sorted arrays due to its logarithmic time complexity and constant space complexity. Mastering this technique is crucial for coding interviews and algorithms.